All right, so we were talking about distribution. So there are some employees like the 20%. So this is the frequency, or and there at the top there is somewhere, okay, 100% or one. All right, so how many people we say have a salary of 10,000, $1,000? I'll say, okay, only 1.5% or the total, or we can say, okay, there's a small people, there are some number of fraction who have a salary between 1,000 and a range like 1,000, 1,500. And then there are some who have a salary of, um, 2,000. And then there are some who have a salary of this, and then there's a 30% or some people have a salary of above 3,000, and very small fraction has a salary of above 3,500, and very small people, small fraction like less than 1% or 1% has a salary of around 4,000. So out of 2,500, only 1% has a salary of 4,000, and 1% has a salary of around 1,000. So this is the distribution, or the shape, we can call the shape of the salary. There are two things which every distribution, two things which can explain the distribution or the shape. So the main thing is what kind of a shape they have. So what kind of, if you make a histogram of the salary, what kind of shape it has, or we can say, if somebody asks you what is the distribution, you can say what is the expected value and variance or standard deviation of that characteristic or that parameter. So there are two things, expected value and standard deviation. Expected value is also the average, EX. It is given by 4 discrete items over n. By summation, I mean I is going from 1 to n, summation. So each item salary, so this is x, xi is 1, x1 is a salary of first person, x2 is the salary of second person, over n. N is the total number of people in the sample or the population. So the point estimate, or yep, sorry, the second thing which defines a distribution is the standard error. Oh, standard deviation, I'm sorry. Standard deviation. So standard deviation is the is calculated by xi minus x bar. So this is also equal, we call this x bar over square over n minus 1. All right, so, and here comes the summation. So we have to understand this thing and this formula. If you don't know, you guys should go back to chapter number 5 and understand this pretty well. So how to operationalize the formula, or how to, so what exactly we are saying here, this is the average, or this is the mean value. So mean value, so we are subtracting mean value from each of the individual salary. So there's a mean salary. So we found the mean salary or the average salary, and then we are saying, okay, let's find out how far they are, how further they are from each other. So for example, I will just put there are employee. So there is employee 1, 2, 3, 4, 5 employees. This is just hypothetical data. So this is their salaries, which I am denoting by XI. So the first employee has a salary of $1,000. The second one has 2,000. Third one has 1,500. Fourth one has 4,000. Fifth one has only 500. All right, so we can find X bar. We can easily find X bar, which is like 1,000 plus 200 plus 1,500 plus 4,000 plus 500, and it comes out to be 0 0. So 5 5 2 3 4 5 6 7 8 9. All right, 2 3 4, yep, 9,000. So 9,000 divided by 5, which comes out to be, all right, so this is pretty much wrong. All right, so it goes here 1,800. So the average salary of an employee, so the average salary in this company comes out to be $1,800. All right, so this is like average salary. So this is X bar. Now we can actually find out. So I will erase few things. So I'll just erase. Just to make some more space. All right. All right, so the fourth column, so we have the xi. We can compute this part. I don't know why it's not working. It's just working pretty weird. So I'm not sure why it's happening, but it's just happening at random. I just want to be careful. I don't want to keep. So, all right, so let's do it again. So this is X, my XI. Oh no, I don't know why I just messed up. So this is XI minus X bar. So we are and then taking a square. So 1,000 minus 1,800 whole square, 2,000 minus 1,800 whole square, 1,500 minus 1,800 whole square, 4,000 minus 1,800 whole square, and 500 minus 1,800 whole square. So we can compute this pretty easily, and which comes out for the first one is 800 whole square, so it comes out 64,000, 64 640,000. So 2,000 minus 1,800, it comes out 200 square, which is 40,000. 300 square, 90,000. So 4,000 subtract 1,800, 2200, and then you square it, so it comes out 484,000. Okay, and then you have 1800 minus 5000, which is 1300 square. So 1300 square, it comes out 169,000. So we have all this. We can actually sum this up, and if we put a summation here, so this we can add them up. So we can add all of them, because we are right now we are putting a sum outside, so we are doing summation. So plus 484,000 plus 90,000. So I'm just summing up from bottom up. 90,000 plus 40,000 plus 64,000. So it comes out a really huge number. So it's like 730,000. Okay. Now I will divide this number by n minus 1. So we have 5. I'll divide by 4 because n is total 5. 4 minus 1 is 5. So I will divide this by 4, which comes out to 825000. And next I'll take a square root of it, and it comes out to be I'm just trying to get this. It comes out to be 1350.92. All right, so this is, we got standard deviation. So this is standard deviation, which means on average, how far is each value from the mean? So standard deviation technically means, or in simplest word, how far a value is away from the mean on average. So generally speaking, on average, each value is $1,350 away. So this is like a dispersion. So if this is the mean, and this is the mean in the middle. So there are some values which are here, some are very close to the mean, but some are very far and some are very near. So this is like, so these are like on average, this distance between each value, on average, the distance from the mean is almost 1350. So this shows that, okay, so we got two things. We got an average, we got average value of the whole data, and we got standard deviation. So we have two things, and these two things can actually explain everything about the distribution, a lot of things about the distribution, or can explain what is the shape of the distribution, what is the shape, or how the data is spread. So the shape means how the data is spread, or it can also make us predictions, and a lot of different things we can do by just calculating two values, like expected value and standard deviation. So always remember how to calculate expected value and standard deviation. So since this is a sample, so this is a very small sample, so this is fine, but and this is n minus 1 is used. If this is standard deviation of the population, we have a slightly different formula. It does not include n minus 1, it has just n. So we divide by total number of elements in the relation, not by -1. So we do divide by n if we are calculating for the population, standard deviation for the population. All right, so however, we are at this point estimate. So So we can um, we can take a sample. So we were talking about taking SRS, or simple random sample, from the population. So assume, for example, we had that salary data. So this salary data, and we took a sample of 30 employees, and we say, okay, we took a sample, and then we say, okay, what are their salaries? So we summed those 30 employee salaries and divide them by 30. This comes out to be 51,818. You can do this, and you can actually find this in Excel. So you can actually do it exactly the way I did. Sum all the salaries. In Excel, you have to use a function called sum, and you will select range. You will open a bracket. You will put equal sum, select the range, and then close the bracket. So this will come. So this will give you a sum divided by n. Okay, which is this. Or in Excel, you can also use the function average. So this will give you Xbar, average. So this is for Excel. So you put an equal sign and then type average and select the range. Select the range of the value. So the whole column will be selected here. You will get the average value of this thing. While you will be doing your work on Excel, if you have downloaded this file and you will be working on this file, you may see different numbers. So since it's randomly generated numbers, so maybe a different number will come on top here. So you will not see same number. So employee number 812 will not be at the top. 1411 wouldn't be the second or third employee in the list. Maybe there will be someone else, because it's just random. That's why it's called random. When you will generate based on your computer, you will not get the exactly same random numbers. You will get different random numbers, even if it's by the same software, because every time you will generate this number, it will be a different number. That's the purpose. I will get a different list of numbers. But your average will come very near to this one. And you can see that we will talk more about it later, but the average comes out to be very near, not exactly, if not exactly like this, but very near to this number. All right, so then are not really huge difference. You wouldn't see a $30,000 or $40,000 salary unless you keep trying, and you generate new numbers. Sometimes you will see, but a lot of time you will see number very near to this one. So this is the sample mean, and there is a standard deviation. And you can also see, okay, so there was in the sample there were two kinds of employee. One of them got the training, one of them didn't get the training. So in your sample, who got the training, so you can say proportion of them, you can find the proportion who got the training, all in sample. So the proportion is like 19 people got the training, there were total 30 people in the sample. So the proportion comes out 0.63. And this number is also important. So we will talk about it, how to use all of them later. So the average salary comes out 51,815 on average in the sample. The dispersion, the spread of the data is 3,000. The salary is spread over $3,384. And these are all, so all these things are called point estimates, because once you have a sample, you can make one inference. So you have a 30, you took one sample and you take an average of that sample, and this one sample is just a point estimate. It's one time. If I ask you do a second time sampling, you select another 30 people, again generate the random number, and you will get another point estimate. You will take 30 people, and I'll say find the sample mean, sample standard deviation and sample proportion. How many people actually got the training and their deviation and their mean, their salaries mean, you will come up, okay, slightly different number. That's a second point estimate. So you can keep doing this point estimate. You can take a lot of point estimate. You can keep doing, and you say, okay, I'm not happy. I just want to take one more sample and see what is the average and standard deviation and the sample proportion. Each one, sample number one, sample number two of the mean, sample number three, there will be a mean from here, XS1, then there will be a mean from SS2, there will be a mean from S3, so there will be a mean from each of them, and then you will get points with all of them. This is a point estimate, this is a point, and this is a point estimate. So all of them are point estimates, and they're point estimators. So for example, the sample mean, here they're saying the sample mean X bar is the point estimator of the population mean mu. So as I said in the earlier, like population means are denoted by mu, and their standard deviation is denoted by sigma. So this is mu, this is sigma, and then this is called rho. So the point is, your sample mean is the point estimator. So it's one estimator, or we call sometimes statistic. This is the statistic. This is the number. This is the statistic. This is the point estimator statistic. So this is the point estimator of the population mean mu, and the S, the small s, we call the sample standard deviation, which is the smallest, is the point estimator of the population standard deviation sigma. So it's a point estimator. It just estimates, and it's only one time. We did not even deliberate. So we just took one sample, and it's one time. S is the point estimator. Same thing, the P bar is the point estimator of the population proportion. So how many people in the total population got the training? And you come up, you say 70 people, 70% took the training, and your point estimator comes out at 60%. So we are saying, okay, we took a sample and we saw that 60% have taken a training. So this P bar is the point estimator. And the numerical value we have in all of them, we call them point estimate. All right, so here they are showing us it's same thing. So there are 30 employees, so they have just shown the salary of 30 employees, what they selected using the random sampling, and their salaries and their if they took the training or not. So each employee X1, X2, X3, X4, and their salaries, and then they took a training or not. So this is shown in the table. So now we can talk about, we have the population. The total population was 2,500 because I have seen this data. You guys should also download and check the data. So the total employees in the data were 2,500 employees, which is capital N. And we took a sample of 30 employees by random sampling. We can find the average and standard deviation of the population and see how many of them actually got the training and how many did not get the training. You can also find this from the Excel, all three things. And then in the separate Excel file, you should see what is the average salary of 30 employees. and their standard deviation and their proportion. What we are seeing here, there is some difference. So it didn't come out exactly like this. All right, this is what we expected. There will be some biasness. So you can say that our sample is showing a little higher salary, like $14. Out of 51,000, we have $14 extra. That's pretty reasonable, first of all. But these are called point estimates, and these are called parameter values. So there now we have two things: parameter value and point estimate. So just make sure these two things are different. So these are like actual, these are from the population, these are actual values, and these are estimated. These are actual for those 30 people, but if you take an inference from them, you will call them, okay, these are the point estimates, and these are basically coming from samples. So this is more information like what you should actually do about your target population, and what is good judgment, when do we need good judgment. So this is the point estimate. So this finishes like the first half of this chapter. Most important thing comes up when we say the point estimates. The X bar also has some distribution. They also follow a distribution. So we found a point estimate X bar, and there's another point estimate rho. Okay, what is the distribution of X bar and rho? How can these things have distribution? They are just one values. So this sounds actually weird, but how about if we keep taking the samples? So the first thing in here, the concept comes up is of random variables. The first concept is right. So the concept comes off a random variable, and we are saying, for example, X bar is a random variable because we are not sure the exact value of X bar. For example, when you took a sample, you got 4,000. For example, you get 4,500. When I took it, I got 51,450. When the textbook took the sample, it came out 51,480. I don't know exactly. So yeah, it came out, the sample came out 51,814. So when you took a second sample with a new random number generated, you got a different value. So X bar, this value, so every time you take a sample, so you take 30 employees, it changes a little bit, it changes its value. So you are not certain about the average value. So if you repeatedly take samples of 30 people from 2,500, so your total population is 2,500, and you took a sample of 30 people, and then you took an average salary and you find their average salary, you will get 1 point estimate. Okay, and then you say, okay, randomly pick another 30 people, and then you took another 30, and then you took an average and you got another sample. So you keep building samples, and then I'll say, okay, take 30 samples like that, and you say, okay, that is still easier. we can take 30 samples. For example, if you have a population of 3 million or 300 million, and then somebody say, okay, take 300 300 sample size sample. So take 300 people in your sample and survey them or ask them a question or get this information from them, and then they say, okay, repeat this 100 times. Take 100 random people again and again, like some different people, and then bring me point estimates for all those 100 averages. So you will come up, you will say, okay, I have already made a distribution. So you will create a distribution for Xbar. So Xbar will also have a distribution. So whenever we have to say, okay, X bar follows, so it's this sign shows follows a distribution, and we can say that when it follows a distribution, it must have two things. First thing is its average. So we can say that the X bar, expected value of X bar, and the second thing is standard deviation of the X bar. So it will follow, so I'll write it here. So I'm just trying to write this. This X bar will also have an average. So when you have a lot of different X bars, 1, 2, 3, 4, 5, and I say, okay, make 50 samples, 50 times, you will select 30 people and find their averages, you will actually you can form a distribution. You can find the average salary, average of average. So it's like average of averages. You took a sample, you took an average, and then you combined 30 sample averages and took again an average. All right, or 20 samples, took again an average. So it's an average of average. Similarly, you can find standard deviation of all the samples. So you you take an average salary. So what is the standard deviation of the average salaries? So you get the two things again. So one more time, the sampling distribution of this X bar is the average of the average samples and standard deviation of the average samples, average values from the samples. So you can say that because the various possible values of X bar are the result of different simple random samples, the probability of distribution of X bar is called the sampling distribution of X bar. Knowledge of the sample and its properties enable us to make probability statements about how close the sample mean X bar is to the population mean mu. So if we know the distribution, we can make a statement about the mu. If we have just done one sample, so we have a total population of, for example, 300 million, and we took one sample of 300 people, and we say, all right, that's great. Even we took a sample of 30,000 people, and then we say, okay, we surveyed them. Or for example, for election, there is a party, and they say, okay, what would be the outcome of the people in this district or in Lowell? Okay, and they come up, okay, they say, okay, Lowell has a population of 100,000, and just saying, for example, and then they say, okay, survey 500 people, and then they say, would they vote for this person, this mayor, or not? And they randomly selected 500 people, and then they come up, okay, they find out would they vote or not, and they found on average they will vote them, or there's a 60% chance that they will vote them. But it's just one sample. So again, it's just one sample. So you say, okay, you took 500 one sample, take 500 again a sample, Again, a random sample, you take 10 times, 10 samples of 500 people each, and then find their averages, and then find average of their average. Okay, so we get the average chance of getting selected, divide by 10, the total number of samples. So in this way, we can make a better statement about the the population, which is like 100,000 people, what their average is or what their perception is. So here they're showing the same thing. So they have taken 500 samples from the same data sets, 30 each sample, and their average for the first sample is this. Second time they did this, third time they did this, fourth time, and then 500 times the sample average came out this. This is the proportion. So how many took the training? How many took the training? It's just moving around. So once we have this one, we can also compute. We can also create a table, a frequency distribution table or frequency table in which, okay, we are saying, okay, the number of samples in which the range is between 49,500 to 50,000 or 49,999. So how many sample lie the average is in this range? So how many are in this range? And we find out, okay, two samples were in this range, 16 samples were in this range, 52 samples are in this range, 100 samples are this, and so on and so forth. And we can find relative frequency because there are 500. We can divide 2 divided by 500. This is relative, like very small number exists here. So 15 relative of 500, 15, 52 divided by 500, so on and so forth. We can find these two numbers like this. So once we have find this, we can actually compute using relative frequencies. We can also use frequencies, but we can use relative frequencies. And if you sum them all up, they will become 100% because they're relative to the total, all of them. So comes up at 1. So we can draw this chart. So very small fraction has a salary below than 50,000, and also a small fraction has a salary of above 54,000. And most of the people are in middle range. So a lot of people, like I think the 25% samples are in this range. So in this range, 20, 25 or more than 25, so it's whatever it is, like 20.27. So 27% of the samples have in this range, and very small are here, very small are here. So this is our distribution of the sampling distribution. So this is the sampling distribution of the Xbar. So this is again, so very small people are in, very large number of people are in the middle range, very small samples like less than 2% are have very small, and have a very small number of people in them which have attended the training, and very small people who have not attended the training. So very small, edges are very small, but most people have attended the, whenever we take a sample, a lot of people we find they have a higher percentage of almost 40% have attended the training. So we have to also check in the population how many percentage has actually attended the training. So this one, so sampling distribution is there. Now comes the two most important things. So the sampling distribution. So I talked about this thing that we can find the expected value of the distribution. So So this is the X bar, and we have many X bars, X bar 1, X bar 2, X bar 3. So we can find their mean, which is expected value of the point estimate. So there are many point estimates, and we can find their mean. We can also find their standard deviation. We can find characteristic shape or form. So we can say that the sampling distribution of X bar is the probability distribution of all possible values of the sample mean X bar. So when we say that the sample point estimator equals the population parameter, so when what we found the X bar 1, and then X bar 2, X bar 500 we find, and then we took an average of all of them. So we just summed all of them, divided by 500. We are saying the number we get here is actually equal to the population mean. If you guys remember, when we are taking different X bar, we were getting slightly different answer from the population mean. But when I average all of them again, I get the population mean. I get the actual population mean. These are just the samples, 30 people. These are not 2,500, but there are so many samples. I just took 500 samples. So they actually approach, or they become equal to the population mean. So this is theoretically possible, but the only thing is, if you took 5 samples, you will not get there. If you take an average of 5 averages, it's unlikely that it will be same as the population mean. You have to take a lot of samples. You have to take repeated samples. So if the average of the average is equals to the population, we call this as an unbiased estimator. It's an unbiased, so I made a mistake here, unbiased estimator. Oops, again. So X bar, so always remember X bar is an unbiased estimator of the population mean. So again, the X bar is an unbiased estimator of population average or mean. All right, so which technically means that if you take an average, like expected of the X bar, you will get population mean. Standard deviation. So the second thing comes up is the standard deviation of X bar, which is we have denoted by here. So sigma X bar. Actually, it is not the unbiased estimator. If you take an average of this thing, you will not get so the standard deviation of X bar, or the standard error of the mean, error of the mean is equal to, this is the population sigma over under root n. So this extra, unless you put this thing, this will be unbiased. So I cannot say this is equals to this. So this is the population, this is the sample standard deviation, standard error. And we sometimes call this standard error, because this is just the error, the biasness. This is exactly the biasness coming in each sample. So this is the far away from the each sample we are. So this is the standard error, is actually not, unless I put under root n here. And this is for the finite sample. we should use this formula. So if someone gives me a sample standard deviation and say, okay, what is the population standard deviation? I can just simply sigma equal to under root n x bar. I can do this and compute because I can know how many samples are there, and I can know from my samples this thing. I can find the population standard error. But this is only for finite, and for this is for infinite. I'm so sorry, this is for infinite, and for finite we have a different kind of a correction. So this whole thing comes in for finite, and this one comes in. So this thing is same, but only this extra part comes in finite. So this is called finite correction factor, or yeah, so this needs to be corrected. So here they have given some examples like how to compute the X bar, sigma, X bar, or standard error. All right, so if somebody asks you what is the sampling error, so you should find, so this is the sample, this is the sample standard deviation, and this is the population standard deviation, divide by under 30, and same thing, divide by under 30, and this is the difference. The difference between the two is called the sampling error. This will always come when we have a population or sample size of 30. So this much error you can expect, sampling error. The difference between the two is the sampling error. So central limit theorem states that, or it suggests that in selecting random samples of size n from a population, the sampling distribution of the sample mean x bar can be approximated by a normal distribution as the sample size becomes large. All right, so what this theorem is talking about, like we took samples and take their average, or we find a point estimator. So we took one sample, and then again we took a second one, then again we took a third one. So unless, okay, so there are two things, there are two possibilities. So the sampling distribution of this thing, so we have this, so when the population has a normal, the sampling distribution is normally distributed for any sample size. So we have a sample size of 30 in each one of them. So we took a lot of different samples and we have a 30. And if the original population is normally distributed, which means it has a shape like this, mu, mean in the middle, and then it has shape like this. Some people are on this side, some people are on this side equally, and another, like it should not be shaped like this. So the mean exists here, a lot very small people are in here, and large number of people are in here. It should not be like this. So I'm trying to say the mean is here, so it should not be like this. It should be normally distributed. So then any size sample, like even if it's a small size or large size samples, the sampling distribution of them is also normally distributed. When the population does not have a normal distribution, the central limit is helpful to identify the shape of the sampling. So if the population distribution is not normal, then um, so we can say that if the sample size become large, so if we took like 5 sample, and we took previously 500 samples. If we take 1000 samples, because it's easy to sample people than to still check the whole population. It's easy to take 1,000 sample of 30 people, then ask 3 million people, survey the 3 million people. It's easier to take a lot of small sample. And then we are saying if we have a lot of samples, then their distribution is again going to be normal. Then if it's normal, we can really make a lot of information. We can make a lot of predictions. So it will follow normal. Then we can apply a lot of statistical techniques on it. So here they are showing us that as the population distribution is population 1 looks like this, population 2 looks like this, population 3 is like this. So if we take sampling of 2, sampling distribution of x bar n is equal to 2, so only 2 values, so we get this kind of a shape. Here we get this kind of a shape. Here it's like this. And so look at these shapes of the population. It's very weird, like it's very weird kind of shape. But as we are taking more number of samples, it's approaching normal distribution. So as it take 30, it becomes quite a bit like this one, it was this, and then it's like this. It's pretty big improvement. And this one becomes like this. That's pretty good. So it approaches normal distribution, and here it just becomes like this, which is pretty good. So it approaches, it becomes like a normal distribution. The shape becomes normal, and we know a lot about normal distribution. We know there are a lot of properties about normal distribution. So if the shape is like this, we know how many people are in this region and how many people are in this region. What is the 80% of population will be here. We know already on this. So we will talk about this more here. So here you should understand that sampling distribution of X bar. So this is the sampling distribution of X bar. The average comes out to 51,800. It is equal to the true population mean. 51,800. This is a true population mean. And sigma over under root n. So here the sigma is the true standard deviation over 30. So we found the standard standard distribution, standard deviation of the sampling distribution, and this comes out to be this number. So we can actually construct this graph. Here they're showing if n is 30, we get something like this, but if n becomes 100, it becomes more like the variance becomes small. So the spread is actually the standard deviation, or the spread in the graph. So the spread in the graph is just because of the standard deviation. It's like showing how far, if this is mu or the mean, how far this value is from the mean, how far this value from the mean. So it's like how far is these values from the mean. And then if we make more samples, if we increase the sample size, it becomes little squid. So it becomes like this. It's like the variation goes away, the extra, the standard error. So the error, it goes away. It try to get to the mean. It try to get to the true mean. And this is the purpose. Like we have to find the true mean or get to near to the true mean. Same thing about the proportion, sample proportion. And so interval estimate. So this is again one of the main topics. So this is all about proportion. So everything, the same thing we discussed, proportion and their sampling distribution, how to find the sampling distribution for proportions. And it's just same. There are a few differences here and here. So you guys can read the textbook and understand this. I think the most important part or the most crucial thing is the interval estimation, in which we also talk about hypothesis hypothesis testing. So interval estimation is there, and I think this is the, yeah, hypothesis testing comes later, and we should talk about it. But I will stop this video because this is getting really long. So I will stop this so you guys can watch it later. But for now, I will stop recording.